Today we are going to discuss about MCQ for GATE exam, entrance test, government exam, GPSC, and this is the part 4 from bending and shear stress. So welcome to my YouTube channel Mechanical Engineering Management. Like, share and subscribe. So let's start from the question number 1. The transverse shear stress acting in a beam of rectangular cross section subjected to a transverse shear load is option variable with maximum at the bottom of the beam, variable with maximum at the top of the beam, uniform across the section, variable with maximum on the neutral axis. So first of all, consider the rectangular section, and this is the neutral axis of the rectangular section. And now I am going to draw the shear stress distribution diagram, and this is the reference line. And you know that shear stress having parabolic nature and it is maximum at the neutral axis. So I can say over here tau max, and shear stress is 0 at the top layer as well as at the bottom layer. So that I can say this is the shear stress distribution. So from this figure you can say the shear stress having maximum value at the neutral axis and it will be vary. So D is the right answer. Next, a block 100 mm by 100 mm base and 10 meter height. What will be the direct shear stress in the element when a tangential force of 10 kN is applied to the upper edge to a displacement 1 mm relative to lower face? Options: 1 Pascal, 1 megapascal, 10 megapascal, 100 Pascal. So consider the block 100 mm by 100 mm base and height 10 meter. So I am going to show the dotted line so that you can visualize the block, and the dimension is given to you 100 mm by 100 mm, that is the base, and height that is also given to you 10 mm. So this is the height 10 mm. Now when a tangential force of 10 kN is applied to the upper edge, so I am going to apply the tangential force to the upper edge, and so that it will be by default at the bottom layer Ft, tangential force, and that is in the form of reaction of this tangential force. So now you know that shear stress tau is equal to load upon area, where load is always the tangential force, and here this is as a tangential force and that is acting on this plane. Now I am going to put the value over here. So Ft, that means tangential force, is given to you as 10 kilonewton. So 10 into 10 raised to 3 Newton divided by area, that means this blue color plane, because of it is tangential force acting on this plane. Now you can imagine the area of this plane as a 100 mm by 100 mm. So I can say over here 100 into 100. And if you simplify, then you will get 1 Newton per mm square, because of I have put the value of area as a mm square. Now you know that 1 Newton per mm square is equal to 1 megapascal. So here B is the right answer. Next, a beam is said to be of uniform strength if option bending moment is same throughout the beam, shear stress is the same throughout the beam, deflection is the same throughout the beam, bending stress is the same at every section along its longitudinal axis. So look at this note. Beam is said to be uniform strength if at every section along its longitudinal axis the bending stress is same. So in short we can say for uniform strength of beam means every section along the longitudinal axis the bending stress should be unique. So D is the right answer. Next, which stress comes when there is an eccentric load applied? Option: shear stress, bending stress, tensile stress, thermal stress. So look at this note. When there is an eccentric load It means that the load is at some distance from the centroidal axis. This causes compression in one side and tension on the other, and hence it causes bending stress. So here B is the right answer. Look at this figure. Here this is the centroidal axis of this element. If the load is applied over here, then it is called as the direct load. If it is with some eccentricity to the centroidal axis, then it is called as the eccentric load. And here this eccentricity is only on one axis, and so that it is called as the compression with uniaxial bending. If eccentricity is on both the axes, then it is called as the biaxial bending. So in short, if I applied the eccentric load, either it is uniaxial or biaxial, it will create the bending stress. So the figure is like that. If I applied the eccentric load, then on one side it will be compressive and on another side it will be tensile stress. And combination of these two stress is called as the bending stress. So B is the right answer. Next, what is the expression of the bending equation? Options are as follows. If the beam is subjected to the bending, so initially the cross section is like that, and after bending it will be like that. This equation is known as the pure bending equation. M by I is equal to sigma by Y is equal to E by R, where M is the bending moment, I is the moment of inertia, sigma is the bending stress, Y is the distance from the neutral axis to the fiber, E is the Young modulus, or sometimes it is called as the modulus of elasticity, and R is the radius of curvature. So you need to remember this very important equation for the bending. So I have written over here this all nomenclature, and you need to understand for the numerical portion. So A is the right answer. Next, consider a 250 mm by 15 mm by 10 mm steel bar which is free to expand is heated from 15 degrees Celsius to 40 degrees Celsius. What will be developed? Option: compressive stress, tensile stress, shear stress, no stress. So look at this important note. If we resist to expand, then and then only stresses will be developed. Here the bar is free to expand, so there will be no any type of stress, because of it is written over here free to expand, and so that no stress will be there. So D is the right answer. Next, the shape stress for a hollow steel column which carries an axial load of 2100 kN is 125 meganewton per meter square. If the external diameter of the column is 30 cm, what will be the internal diameter? Option: 25 cm, 26.19 cm, 30.14 cm, 27.9 cm. So here hollow steel column is given to you. So consider this is the hollow steel column, and that is subjected to compressive load, and that is given to you 2100 kN. So I can say compressive stress is equal to load upon area. So put the value of 125 meganewton per meter square, and keep in mind that it is meganewton per meter square. So if I multiply it by 10⁻�3, then it will be kilonewton per meter square, because of load is given to you in kilonewton. So it must be in kilonewton per meter square. And so that P is equal to 2100 divided by area as it is. So if you simplify, then you will get A is equal to 0.0168, and the unit is meter square, because of we have taken sigma C as kilonewton per meter square, and so that your area is in meter square. Now you know that for hollow circular column, area is equal to pi by 4 capital D square minus pi by 4 small d square. So I can start with this equation. But here the external diameter, that means capital D, is given to you as 30 centimeter. And over here our area is in meter square. So first convert it into centimeter square. And then I can use it over here, is equal to pi by 4 as it is, and D is equal to 30 centimeter minus D square, where D is the internal diameter. So if you simplify, then you will get small d is equal to 26.19 centimeter. So B is the right answer. Next, for keeping the stress wholly compressive, the load may be applied on a circular column anywhere within a concentric circle of diameter dash. Option d by 2, d by 3, d by 4 and d by 8. Now look at this figure. This is the column and this is the compressive load, and that is with some eccentricity. So consider a circular column having diameter d subjected to load P at eccentricity E from center as shown in figure. For a circular section, diameter of kernel section is always d by 4. Sometimes it is called as the core section also. So if I look at the top view of this column, then it will be like that. Capital D is the diameter, and this circle is called as the core section of the column, or sometimes it is called as the kernel section of the column. So in this particular concentric circle, if you apply the compressive load, then the material will be subjected to only compressive stress. So this portion is known as the core section or kernel. So if the load application on a circular column is under d by 4, that means under this circle, the stress will be wholly compressive. So C is the right answer. Next, consider two bars A and B of same material tightly secured between two unyielding walls. Coefficient of thermal expansion of bar A is more than that of B. What are the stresses induced on increasing the temperature? Options are as follows. Now look at this note. Since both the supports are fixed and both bars will try to expand, so rise in temperature will cause compressive stresses in the bar. So very simple. If both the walls are unyielding, that means there will be definitely the compressive stress in the material due to the thermal expansion. So compression in both the materials is the right answer. Next, for a circular shaft of diameter d subjected to torque T, the maximum value of the shear stress is option 64T upon pi d cube, 32T upon pi d cube, 16T upon pi d cube, 8T upon pi d cube. So you know that fundamental equation of the shaft subjected to torque T is equal to pi by 16 tau d cube. So from this equation, if you find the maximum value of shear stress tau, then it will be 16T upon pi d cube. So C is the right answer. So thanks my dear friends. Press the like button to appreciate this video.